Hello everyone, welcome to my Six Sigma in Actions video series where we cover real life case studies of Six Sigma with Minitab. In today's chapter, we will be covering hypothesis testing and how hypothesis testing can be used when you feel something's off with the process output. It helps you dig deeper and find the underlying reasons of what is wrong with the process. And we'll see an example of that, a case study. Imagine you are a process engineer at a manufacturing company. This is the define phase, and you feel that something's off with the process output for a particular category of products. So you decide to perform some quality checks specifically for three things: the proportion of defectives within the population for a particular product. Here, the test you put in place is to check if the proportion of defectives for the entire population is less than the targeted 5% or is it more. So the null hypothesis developed is that the population proportion of defectives is 0.05. The alternate hypothesis, it's less than 0.05. The other quality check you wanted to do is the performances of a particular machine. Here, the test is to check whether the length of the product coming out of machine Q, if it is equal to the targeted 10 inches. You have a suspicion that it's less than 10 inches. So the null hypothesis is product length from machine Q equal to 10. Alternative hypothesis, the product length from machine Q less than 10. And finally, one more thing you want to check as part of this quality control is comparison of the output coming from three different shifts. The specific test that you are creating for this is to check whether the mean diameter of the products is that same across all three shifts. Null hypothesis, process mean from shift 1 equal to process mean from shift 2 equal to process mean from shift 3. Alternative hypothesis, these process means are not equal. And that is the define phase for this case study. Okay, so our next phase is the measure phase. We will be covering all the three tests in the measure phase. Our first test is to check if the population proportion of defectives is less than the targeted 5%. For this, a sample of 200 products was taken from the process, and turns out that 3 out of those 200 were identified as defective. So now we have a proportion for the sample, 3 out of 200, of defectives versus total. Now we need to extrapolate this for the entire population. And for that, we use one proportion feature in Minitab. And I'll show you how that was done on Minitab. So to use one proportion, we go to stats, basic statistics, go to one proportion, and you can use summarize data. Since the number of defectives, the number of events were 3, you mentioned 3, number of trials, the total is 200, and you also perform the hypothesis testing since you have that targeted 5%. And we've already discussed the null hypothesis and alternative hypothesis in these cases. The, and so hypothesis proportion of 0.05 is set. In options, you can set the confidence level at 95. Since you're interested in the alternative hypothesis being less than 5%, so you set the proportion less than hypothesized proportion, and this also gives you the upper bound of the confidence interval, which is probably what you're interested in since you're testing the targeted 5% and less than 5%. And the method you can use is normal approximation. This is a good method when the sample sizes is pretty good. It's a large sample size of 200. and you hit OK, and there you go. So since the p-value is 0.012, which is less than 0.05, we have to accept the alternative hypothesis and reject the null hypothesis. It also shows you the upper bound of the p-value, 95% upper bound, which reaches up to 0.029. Again, doesn't reach the 0.05%. So it does tell you that the alternative hypothesis is true, and which is a good thing, that the proportion of defectives in the entire of the population has not reached 5%. It's less than 5%. And that's it for test 1. So now we come to our test 2, where we are checking whether the length of the product coming out of a particular machine q, is equal to the targeted 10 inches. 10 inches is what is desired, and we have a suspicion with this machine that it's producing products less than 10 inches. So what we do is we take a sample of 20 products coming out of this machine and check the lengths of these products and compile a data based on that sample data. Because the sample size is less than 30, we can use one sample t-test on Minitab to extrapolate this sample information onto population and see if the confidence interval on the population falls around 10 or less than 10. Again, the null hypothesis is that the length of the product is going to be equal to 10, and the alternative hypothesis is the length of the product is going to be less than 10. And I'll show you guys on Minitab how we're doing this test. So here I've already populated the 20 samples data from machine Q, and I've created a separate tab for test 2. To do one sample t-test, you go to stats, basic statistics, you go into one sample t, and you populate machine Q here. And for perform, you do want to do the hypothesis testing. Hypothesized mean is 10. In options, you can select the confidence level of 95. And again, since you're testing the alternative hypothesis being less than 10, you can mention that mean is less than the hypothesized mean. And again, this will produce the upper bound, which is what you're interested in, to see at the max, the population mean, how large can that be, and whether it touches 10. You can also do a little graph action to visualize this, and individual value plot would be the best fit here. And with all that done, let's say click OK. And this is what we get. We get a p-value of 0, which kind of tells you that you have to reject the null hypothesis since it's less than 0.05, and we got a confidence level of 95. And you have to accept the alternative hypothesis that the mean is less than 10. Same thing, we see the mean being around 8.8, and the upper bound, 95% confidence upper bound for mean at max reaches to 9.2, not close to 10. So in the best of cases, it's not going to be 10. And that's visualized here in the value, in the individual value plot. Here's your desired mean. Here's the mean we have for population. And here's the upper bound for the population. It's not close to 10. So the conclusion here is that machine Q is definitely producing products less than the desired length, less than 10. and there is something wrong with this machine. It needs to be fixed. Okay, guys, now we get to test 3. In test 3, what we are looking for is that the mean diameter of the products, whether are they same across the 3 shifts or not. That's what we're trying to check. So to do that, we take a sample of 20 products from each of these shifts and measure their diameters. And this is going to be the sample data to perform this test. The process engineer wants to perform the analysis of variance test to check if the mean diameter of the products across all these shifts is same. But to perform the ANOVA test, there are some prerequisites that you have to fulfill. One of those prerequisites is basically to check if the data from the 3 shifts is normally distributed. In the past, we have used graphical summary to check if the data is normally distributed, but since here we have 3 sets of data and we want to do that normality test simultaneously, we will be using something called as probability plot. Let's do that and come back to the second prerequisite. So here I've already created a new worksheet for test 3 and populated the data for the 3 shifts. We got sample data, 20 sample data for each shift. And what we got to do right now is look for the normality test for each of these data sets. To do that, we will be doing probability plot, go to graph, probability plot, multiple, hit OK. We're going to select all these 3 shifts, and since these are separate groups, we're going to check this, and I think that should be good. We can do either separate graphs or overlaid. We can do separate graphs. And what are my options here? Okay, that looks fine. And we hit OK. Let's say it's taking its time. But here it is. So this is the probability plot for all of the 3 shifts. And since the p-value in this case is above 0.05, here it's above 0.05 as well, and in this case as well. So since in each of these the probability plots is above 0.05, we can say that the data is normally distributed in each of these shifts. So that satisfies our first prerequisite. Let's go to the second prerequisite. The second prerequisite is that the data from the 3 shifts needs to have equal variance. And this can be checked using a test of equal variance within Minitab. But to do this test, we do need to stack up the data from 3 shifts into one column and label them appropriately. So let's go and do the test of equal variance in Minitab. So we're going to stack the data from all these 3 shifts into one column called size. To do the stacking, we can go to I got a lag here. We can go to data, stack, column, and we will be stacking the data in the column size, and we've selected all these 3 shifts, and then just hit OK. So here we have stacked the data. It should be up till 60. Yeah. And to label it, let's just label it as shift. It's going to be shift 1 all the way till here. It's going to be shift 2, and then all the way till 40, and then shift 3 from 41. We can just copy this and paste here. Copy this, paste till 39, I mean 40, and then copy shift 3, paste till 60. So there we have it. All the data is stacked and appropriately labeled. Let's go ahead and do the test of equal variance. For that, we gotta go to stats, ANOVA, and test for of equal variance. Response data is all in one column, that's correct. And basically, the response means the effect, and factor means the cause. We know the effect is size, so size is selected here, and factor or the cause is the shift, so shift is selected here. And we get some more options here. We can do a summary plot. What other options are there? An option of confidence level 95, that makes sense. We know the test is based on normal distribution, we just checked. The data is normally distributed, and I think we look good. Let's go ahead. So as we discussed, the null hypothesis of this test is that all variance is equal. Alternative hypothesis is that at least one of them is not equal. So let's see the p-value here. P-value is 0.862, well above 0.05. So we have to accept the null hypothesis, which is that all variance is equal. And here it's been graphically represented. It does look like the variances align. And the overall conclusion here is that the variances are equal. So we've kind of satisfied both our prerequisites for doing the ANOVA test. So let's go ahead and do the ANOVA test. So the data is for three shift is normally distributed. The data across the three shift have equal variance. Now to perform the test 3, all we got to do is the ANOVA test, and that can be done by going to stats, ANOVA, and one way. The reason we are doing one way ANOVA is because we have one factor and one response. So to do the ANOVA test, go to stats, ANOVA, one way, and responses. The response data is in one column. That's correct. Like I said, the factor is the cause, which is shift, and the response is the size. We can do a graph of interval plot. Other options are assume equal variance. We did test that, and a confidence level of 95, and a confidence interval can be two-sided. That's fine. And just hit OK. Okay, so here for this test, the null hypothesis is that all means are equal. Alternative hypothesis that all means are not equal. And the p-value we've gotten is 0.058, meaning that we have to accept the null hypothesis of all means being equal. Gives us a nice confidence interval. They look very aligned across the three shift. Even the mean is pretty aligned. And here's a graphical representation, an interval plot. So overall, again, the conclusion here is that the null hypothesis has to be accepted. The mean diameter for the product across three shift is equal. So we do not see any issues with the shifts. So we covered the define phase in this chapter, and the measure phase and analyze phase was kind of combined. Now let's get to the improve and control phase. Based on the three tests we did and the outputs from that test, we realized that the only issue we had was with machine Q, and the machine Q was fixed, so the process was improved. And as part of the control, the process engineer will continue taking samples of all the machines and all the shifts to ensure that the improved process is remains under control. That completes the improved and controlled phase for this case study. So this concludes the entire chapter of hypothesis testing for quality control. Thank you so much for watching, and I'll see you in the next one.